Well, greetings, Mr. Kolazar's class. We're going to continue with our bonding of electrons. We've talked about ionic, we've talked about metallic, and now we're going to look into covalent bonding. So we're going to describe the formation of covalent bonds with this section, also known as molecular compounds, and we're going to compare and contrast the difference between ionic and covalent will be the big parts of this section. So to get us started today, covalent compounds. Compounds that are composed of covalent bonds, just like ionic compounds are composed of ionic bonds. These are sometimes known as molecular compounds. So anytime we see the word molecular compound or molecule, we're going to know that it's made of covalent bonds. So a molecule or a covalent bond, same idea as we're going forward there. So covalent bond is going to be made by the sharing of electrons between the two atoms, because they have similar abilities to attract bonding electrons. Both of them want electrons, so they're going to share them instead. So covalent bonds occur between a nonmetal. Remember, stair-step line. Nonmetals are to the right of the stair-step line, so they're in that upper section here, is where we're going to see those metals or nonmetals bonding together. Sharing is caring. Caring and covalent would be a way to remember that covalent bonds share electrons. So to form a covalent bond, summary for formation of a covalent bond, elements both have a decent pull for electrons, so they don't want to lose them easily. Both atoms compromise, and they're going to share valence electrons to get to their full octet. So they want 8 electrons, except elements 1 through 5 only want 2 electrons. So they're a duet instead of an octet. But they're going to end up sharing those electrons because they both want to pull on the electrons. So we've got a nice diagram there right below number 4 in your notes. What we're looking at here is both atoms will bond when there's a balance between the attraction for the other's electrons from the other's nucleus. So one's electrons are going to be attracted to the other's nucleus. And then we'll look at the repulsion of the nuclei. I get too close in a second. So we've got kind of the electron cloud of one and the electron cloud of the other. And we've got the positive in the center. So our electrons on the outside are going to be attracted to the nucleus of the other. And as they start to get closer and closer, that attraction starts to get a little bit greater, and eventually they get to the point where it's right in between, where the positive of one and the negative of the other, and instead of being two separate clouds, those clouds kind of overlap, and the electron is going to be attracted by both nuclei. And so instead the electrons are going to be in the valence shell shared between the two. Now if we do get too close, they start pulling too close together. Remember, the positive opposites attract but likes repel, and if they get too close then they would push away from each other. So there's this just right area of where the electron clouds overlap because the electrons of one atom are attracted to both nuclei. Electrons of the other atom are attracted to both nuclei, so they share time around both atoms, those valence electrons. So sharing is caring. Now a couple ways we're going to show this. Next chapter we're going to really focus in on our Lewis structures for demonstrating covalent bonding, but just to kind of show a coming attraction. Chlorine, 7 valence electrons. It's in group 7-3, single, 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 paired, paired, paired. And if another chlorine, Cl2, so we have 2 of them. Now, last chapter with ionic, if one electron was to be moved over to here, we would have 8 total electrons, but then the other chlorine atom would only have 6 and it wouldn't be happy. So instead, what's going to end up happening is this valence electron is going to come and be shared with that atom, and that chlorine atom is going to share one of its valence electrons back with chlorine, and that shared pair of electrons, sharing, remember, if I'm going to share with one atom, that atom has to share back an electron to be considered sharing in the covalent world. In the end, we're just going to pull those two close together with one line being shown there. And that one line, that's one covalent bond. And we're going to know that to be 2 electrons are needed to make that up. So there are 2 electrons being shared is that symbol for that line in between the two. If we wanted to, we could put the outer electron still in, but we're focused on that one line between those two. That's 2 electrons being shared. And if we were to look then, we would have our 8 electrons around one atom. And if we took that one and circled through, we'd have 8 electrons around it to be that octet. So that bond in the center there, that's those 2 shared electrons, one from each atom. We'll try one more. So water, H2O, 1 oxygen. So oxygen has group 16, 6 outer electrons. And hydrogen only has 1 outer electron. Now hydrogen, 2H2, 1 outer electron, wants to go with the duet, not the octet. It only wants 2 outer electrons. So we're going to share, and we're going to share. Now at this point, notice if we were to look around, the oxygen has 1, 2, 3, 4, 5, 6, 7, 8 outer electrons total now being shared. This hydrogen and this hydrogen both have 2 outer electrons being shared total now. So they're both happy too. So one way we could draw this out, H to oxygen, and we have our 2 outer electrons and our second pair of outer electrons there. So that's a covalent bond also. 2 shared electrons and 2 shared electrons to get that. These are some lone pairs of electrons in oxygen we'll talk about here shortly. It's a little bit more negative here because of that overall, but we're going to worry about that a little bit later. Ammonia NH3 and methane CH4, we're going to work on those ones a little bit later on. We just wanted to kind of get a little picture overall of what we're looking at, sharing of electrons. So we're going to look at the bonding, covalent bonds. First, what we're going to know is intermolecular forces. You're going to hear this word IMFs a lot throughout the year. It's the forces holding one molecule to another molecule. So IMFs, intermolecular forces. So we're going to start out again with bonds. And to look at it, the one we did before, water, HOH, lone pair of electrons, lone pair of electrons. Covalent bond is between the atoms to make the molecule. So 2 electrons shared. Oops, 2 E minus shared. So what we're looking at here is this would be a covalent bond, and this would be a covalent bond. So they are connecting the 2 atoms together to make the covalent bond. Now, if we were to take that idea and go a little bit further, and the next part would be that we have our water, HOH. Now these lone pair of electrons here have a little bit more of what we're going to call a partial negative to them. And on this side, the hydrogens have kind of a little bit more partial positive. The symbol here that I'm drawing is called sigma. And it's going to be known as our partial charge as we're going forward later on. So sigma is going to be a term or a symbol that we use coming up. It kind of looks like almost like a little squiggle D. Kind of almost looks like like a little firecracker there with a fuse on the top. But it's going to tell us partial. So the negative electrons on this side are pulling kind of a negative charge overall to this side and a little bit more of a positive to this side. So what's going to end up happening is the positive of one and the negative of another. If we were to find another water it would kind of maybe line up. Here, where we would have lone electrons and a partial negative to this side, partial positive to this side, and the intermolecular forces between them, we're just going to show some dotted lines here. There would be an attraction force between that positive and that negative, and that positive and that negative. And if we wanted to, we could draw probably one more water, OH. Where that negative partial part here is going to attract to that positive. And this is going to be our IMFs. Intermolecular forces are what are holding two molecules together. So intermolecular forces, IMFs, hold molecules together. Now as we're going, these are very weak. Covalent bonds are very strong. So we'll continue to look at this in class. We talked about earlier this year doing a belly flop into the water. You do a belly flop into the water and you hit the water, you're breaking apart these intermolecular forces as you go through the water that are easily reformed. It hurts a lot. The force need to break those. You don't break any of the covalent bonds when you do a belly flop. They're much too strong for that. So it will be something we continue to look at throughout the year, intermolecular forces. So properties, covalent bonds, atoms held together in the molecule are very strong. So our covalent bonds are very strong. Intermolecular forces, those IMFs, are very weak, which is the reason why we have low boiling and low melting points. They're also very soft, easy to scratch. Covalent compounds dissolved in water are molecules. They're neutral overall, so they cannot conduct electricity. They don't have that plus minus like the ionic compounds have. So for some good comparison, we'll need to know this chart. Type of bond, covalent bond makes covalent compounds, ionic bonds make ionic compounds. We share electrons for covalent. There's a give, take, or transfer of electrons in ionic. Types of elements, nonmetal, nonmetal, both on the right-hand side of the periodic table. Metal, nonmetal, a left and right-hand side of the periodic table on that stair-step line. Smallest particle, if you just have one, is known as a molecule. If you just have one ionic compound, like one crystal of NaCl, just have one of it, it's known as a formula unit. Strength of forces, both of them are strong. However, weak intermolecular forces holding the two molecules together. State at room temperature, because of those weak intermolecular forces, solids, liquids, or gases for covalent compounds. Strong forces hold ionic bonds together, always are solids at room temperature. Low melting points because they could be solids, liquids, or gases for covalent. High for ionic compounds because they're all solids. Cannot conduct electricity under any situation. Only if they're dissolved or melted can the ionic compounds make, because they make that plus minus interaction of which the electrons are allowed to flow through. And just to end the hour with, covalent bond yells at an ionic bond. Didn't anybody ever teach you to share? Sharing, remember, is caring. So caring for covalent compounds.